Welcome to our next lecture in elementary statistics at Dallas College, specifically with Professor Bailey and using Alex. We're looking at Chapter 7.1, Confidence Intervals for a Population Mean. We have described statistical analysis as a four-step process whose steps are to formulate questions, collect data needed to answer the question, describe the data, and then draw conclusions using the appropriate methods. We now discuss the construction of what's something called confidence intervals, which are the most commonly used methods for drawing conclusions. In my lecture classes on campus, the students also do a group project which actually goes through all these four steps, so that's what this is referring to. A point estimate. A simple random sample of 100 fourth graders is selected to take part in a new experimental approach to the teaching of reading. At the end of the program, the students will be given a standardized reading test. Suppose that the mean score for the 100 students in the program was 67.3, and remember we notate this with X bar. Now the administrators want to estimate what the mean score would be if the entire population of fourth graders in the district had enrolled in the program. Right now, the best estimate for the population mean is the sample mean. X bar equals 67.3, and this is what we call a point estimate. When we don't have a value for a specific measure, like for example the average score, we often will use a sample to create that estimate. It's very unlikely that the mean 67.3 is exactly equal to the population. This is just common sense. Typically, the larger the sample we have, the closer it's going to be to the population. Okay. In order for the estimate to be useful, we must decide how close it is likely to be. For example, if we think that it could be off, say, 10 points, we would estimate the population average would be in the interval between 57.3 and 77.3, plus or minus 10 points. This can also be written as 67.3 plus or minus 10, and this plus or minus number is called the margin of error. The interval used to estimate the value of the parameter is called a confidence interval. Suppose that we require a certain level of confidence, say 95%, that the interval contains the population mean. The real question is, what should the margin of error be in order to have 95% confidence that the population mean is within this entire interval? The margin of error for any level of confidence can be found using the sampling distribution of X bar, which we looked at in the prior section and chapter. We begin by finding the margin of error for a 95% confidence level and then generalize the method. Recall the previous techniques we used to find the z-scores that bound 95% of the area under the standard normal curve, right? Remember that 95% of all data, if you have a normal curve, is between plus or minus 2 standard deviations. You can see that here. The z-score here at plus 2 standard deviations is 1.96. And remember this, we would look in the table then to find the area inside there, right? This would be not 95, because if we have 95% here between these two dark tails, that means we have 5% left in both tails, or 2.5% in just one tail. So how do we find this z-score? Well, if this is 2.5% in the right tail, remember the z-score at this point gives all of the area to the left which would be 97.5% or 0.975. If you look in table A2 and look for that value in the table, 0.975, you will find the z-score for that is 1.96. Okay? And this is just going through that area. So Z1 is negative 1.96, Z2 is 1.96, and 95% of the area is bounded within 1.96 standard deviations plus or minus. This number is called the critical value. When the sample size is large, and specifically we're talking that it's greater than 30, the central limit theorem tells us that the sampling distribution of x bar is approximately normal with mean mu and standard error sigma sub x bar. Because the sampling distribution of x bar is normal, 95% of all sample means will lie within 1.96 standard deviations of the population mean. So this is how we will take that point estimate and make sure that we're 95% confident that our population mean is in that range or interval. That is mu minus 1.96 times the standard deviation, plus or minus that, mu plus or minus 1.96 is the interval for all sample means. Okay? With 95% confidence, the population mean is contained in x bar plus or minus 1.96, the standard deviation of x bar. And again, that means the margin of error is 1.96 times the standard deviation. Okay? In general, the margin of error will be in the form, the critical value, that was the 1.96, and the critical value is based upon what confidence level we want. For example, if we only need an 80% confidence level, this critical value will change, right? If we want 80%, that means 10% is in each tail, because it's 20% total under the curve. And then this right x value, if we were trying to find the z-score, would be, since there's 10% here, we'd be looking at 90% or 0.90 in the table, and then we would find the z-score that would give us this critical value. For the example on the new approach to reading, suppose that we know from past results that scores on the standardized reading test have a population standard deviation of 15. Find the standard error, the margin of error, and the confidence level. And I've given you those formulas here. Okay? The standard error is simply, remember from before, it's the population standard deviation over the square root of the sample size. And here we have the calculation. The margin of error, we've already figured out that the critical value is 1.96 times the standard error, which is 1.5. We just calculated 2.94. Therefore, a 95% confidence interval for the population average is plus or minus this value. Our sample mean that we found, which I've listed up here in the right, plus or minus the 2.94. Okay, so we have x bar minus 2.94, x bar plus 2.94, x bar was given to us when we took our sample, etc. So we have a 95% confidence level, or we are 95% confident that the population mean is between 64 and 70, basically, for this standard reasoning test. All right? So it's important you know how to calculate these three different measures and then report a confidence level. Point estimate is a single number that is used to estimate the value of an unknown parameter. This is, again, the idea. We take a sample to use that as an estimate for the population. A confidence level is an interval that is used to estimate the value of the parameter. So again, we don't know, we can't say for sure that what we calculated or found in our sample or our survey, etc., is true for the whole population, but we can use this confidence level to get a interval that we feel pretty confident that that value is in there. Again, the confidence level is a percentage between 0% and 100 that measures the success rate of the method used. And again, why you would use really low confidence levels, I can't even imagine. Typically, it's about 90 or 95%. The margin of error is computed by multiplying the critical value, which is the z-score for a specific confidence level, by the standard error. Although 95% is the most commonly used confidence level, sometimes we want to construct a confidence interval with a different level. It really depends on what your study is. The more important the accuracy is, like let's say you're doing a study about the efficacy of medicine, you want to be pretty certain of that. Versus maybe the joy that a child finds from playing with a specific type of toy, that may not be so important. It's not, there's no really dangers, etc. We can construct a confidence interval with any confidence level between 0 and 100% by finding the appropriate critical value, which we just went through that exercise. You have to understand the normal curve. You have to understand what z-scores represent, and you need to know how to use table A2. Table A3, which is also in your online eCampus either under tests or Bailey resources, does provide confidence levels at the bottom, and we're going to look at this table A3 later on. Okay, so here are just some. They just because these are so widely used, they just pulled them right out of the table. So 90% confidence level is a critical value of 1.645, 95, 98, and 99. You see them. This is just a little reminder. So if 90% confidence level, right? We want the middle 90%. So that means that we have 10% left in both tails. So we'd have 5% left in each tail. Okay. So really what we're looking for here to find that z-score is 0.95 in the table, and then you'll get this 1645. So here's a problem. Go ahead and try to work through this problem. It's the same type of problem we just saw. A large sample has a mean x bar equals 7.1, and the standard error, sigma over square root of n, equals 2.3. Construct a 90% interval for the population mean. So this one, a lot of the work's already been done for you. You don't need to figure out the standard error. You've got it, and you've got the critical values here. Remember, the margin of error simply is the critical value times the standard error. We multiply those out and get 3.8. A 90% confidence interval then is x bar plus or minus this margin of error. So we plug in the x bar value, do the calculations, and we have our interval for 90% confidence. Notice how this is stated. This is very, statistics as a science has a very specific language we use. We are 90% confident that the population mean score is between 3.3 and 10.9. Okay. So this gets a little confusing. Sometimes we need to find a critical value for a confidence level that's not given in table A3. To do this, it's useful to learn a notation for z-score with a given area to its right. The notion z alpha refers to the z-score within an area of alpha to its right. Z sub alpha over 2 refers to the z-score within an area of alpha over 2 to its right. Okay. So whenever we're talking about a confidence level, we have some kind of confidence level that we're shooting for, right? That's what's in the black here. That's the total alpha. If you are, yes, that is the, not the alpha. Let me rephrase that. This is, let's say it's 90%. Okay. We calculate the alpha by what's left over. So 9 90%, which is 0.9, would give us alpha equals 0.10 or 10%. If alpha equals 10%, that means that 5% or 0.05 is in each tail. Okay? And so this is a way you can figure out the z-score, which we've been doing in all the problems before. If this is, if we're doing a 90% confidence interval, that means 10% is in both tails or 5% is in each tail, then the z-score here is going to represent 95% or 0.95. So we would look in table A2 to find that value as z, which is 0.95. Okay? And that technically, if you did 1 minus that, that gives you that 5%, right? The area to the right. So again, if we wanted to find a confidence interval of 96%, we would first figure out that 1 minus alpha equals this. To me, like, this actually confuses me more, this 1 minus alpha. I know that alpha is the difference left. Alpha is the total that makes up 100%, which is what this is saying, but for some reason putting it in this expression makes it a little more confusing to me. But it is the formula. I just know that if I'm looking for confidence interval of 96%, then alpha is 4%. If I'm looking for a confidence interval of 70%, then I have 30% left, which is what alpha is. Okay. Once I find alpha, then I find alpha over 2, 0.02. And then I can use the table for z alpha over 2 to find the area to the right. But to me, it's just as easy to use the area to the left. And again, the area to the left of this is going to be, we already know this. It's going to be, if it's 0.02 in this area, then this is going to be 0.98, right? All right, so this is actually going through the exercise. If you want to try it, it's a good idea to try it. I actually find that drawing these curves, the normal curves with the tails on each end, helps me visualize. It helps me not make mistakes. Okay, so again, if the confidence level is 92% or 0.92, then alpha is going to equal 0.08 or 8%. And so alpha over 2 would be 4% or 0.04. If we look at that, what we're looking for, if we have 4% in the right tail, then the area to the left of this is 96%. This is the value. You're looking at all those data points inside the table so that you can find the z-score that represents that. And if you look at the table, so we're going to look at all the data in here. We're trying to find 0.96, 0.94, 9582. We're getting closer. Here, between these two values, we can see that 0.9599 is just 0.0001 away from 0.96. That's close enough. So my z-score here is going to be 1.75. Okay. This is important for you to kind of picture this and relate these two different concepts. And so I want to make sure that you get this. As always, in the back of this section 7.1, there's some great step-by-step instructions for technology and some great examples using your TI-84, Excel. I'm not going to be going through these, but you have step-by-step instructions actually in your textbook, and you have the textbook in Alex. In general, though, we've been using a standard deviation known for the population, but typically we don't know what the standard deviation of the population is. The advantage of beginning with this case is that it allows us to use the familiar normal distribution. As I said, normally we do not know what the standard deviation of a population is, but we will learn how to create confidence intervals in this. The assumption for constructing a confidence interval for a population mean when the population standard is known is simply that we have a simple random sample, the sample size is large, it's greater than 30, and the population is approximately. Okay. You can check these out, find the critical value for a 98% confidence level. Again, tables A2 and A3 are in eCampus under Bailey Resources, and I think there's usually a link in the testing folder as well in eCampus. You may use these on tests. I have no problem with you using these tables. Just make sure you don't write on them, and make sure you show both sides when you're doing your environmental scan prior to a test. Okay, here's the answers to both of these problems. I think these are good ones to check or to try and see if you can get the right answer. Again, we have a couple more sample problems here based upon what we've already done. So the first thing we do is verify the assumptions are satisfied. We have a simple random sample. We have 75 students, so that's our sample size. And we know the sample standard deviation. So the assumptions are met. We can go through and construct a 90% confidence interval the way we've done this last exercises. And then what this last question is if this 100 is in our interval, or this is greater than 100, our interval has all values greater than 100, so it's very likely that the population mean. Here's another one. Again, I'm not going to walk through this. I just wanted to give you some practice in here. So it's a chance for you to kind of practice this and have the answers. All right. These are the objectives that we started with: how to construct and interpret confidence intervals, and how to find critical values.